Last week I talked about the physical impact of climate change. Today I'm going to talk about the economic impacts of climate change. Got to pick up one bit of valuation that we didn't do last week because we ran out of time. So this is where we are in the sequence, and this is the actual sequence. I don't know why it does this. So we're talking about the impacts of climate change. We talked about climate policy, and then in 2 weeks we're going to start talking about cost-benefit analysis of climate policy. So before I'm going to talk about estimates of the economic impacts, I'm going to talk about what methods have been used to estimate these things. I showed this particular graph last week, where different people with different attitudes and different value systems look at climate change differently. Some worry about species going extinct, and then climate change is a really big risk. And other people just worry about such things as West Antarctica sliding into sea, and then climate change is much less of a concern. Today I'm going to talk about the aggregate impacts, what happens to the welfare of the average person, and I'm also going to talk about the distribution of these impacts. Earlier this week, on Monday to be precise, the sixth assessment report of Working Group 2 of the Intergovernmental Panel on Climate Change came out. So a lot of the graphs that I showed you last week are now outdated, and there's new graphs out there. I'll put a link on Canvas so that you can update yourself. Not a whole lot has changed. It's just a lot more detail has been added.
Is it good detail, or is it jargon?
Well, the report is 3,693 pages long. Haven't read it all. The overall thrust of the methods is the same as it's always been. There's just lots and lots more details, and actually cramming more and more detail into these reports and these summaries just makes the mind you just can't read it anymore. There's just so much that it's just beyond absorption, I think.
That's the point. It's not tactical.
No, I think it's just institutional momentum that the IPCC is incapable of reforming itself and doing something smarter with the avalanche of information that is coming. That's my opinion. Nobody listens to me when it comes to the IPCC. So let's look at the aggregate impact. I'm going to show this particular graph a number of times. What you're looking at is estimates of the total economic impact of climate change. On the horizontal axis, we have changes in the global mean surface air temperature. That does not mean that we believe that warming is the only thing that matters for climate change, but it's just an index for the severity of climate change, all relative to pre-industrial time. So that's the 0, and now at around 1.1 degrees. And then on the vertical axis, you're looking at the Higgshian equivalent variation. That is, how much does climate change? The way to read this is that 2.5 degrees of warming would make you feel as if you had lost 1.3% of your income, where 1.3% is the average of the blue dots. So that is how to read this graph. The blue dots are the 27 primary estimates that were published 3 years or more ago. And then the red curve is just a curve that is fitted through this, right? So I'm going to talk about this graph for a long time. But the first question is, where do the blue dots come from? How did people actually estimate this? Well, people have been using four different methods, and the first one and the most popular one is the so-called enumerative method. This was designed by this guy here, Ralph Darts, seen here in his better days. And essentially what you do in the enumerative method is what I did last week. You go through the list of impacts of climate change. You quantify them. So you say, well, wheat yields are going to fall by 20% and rice yields are going to go up by 10%. There's 10 million square kilometer that's going to be lost to the sea. We're going to build 1,000 kilometers of dikes, and so on and so forth. So many people will die prematurely, and so on and so forth. So that is what you do. That's your first step. You quantify those impacts in their natural units. Then you estimate the price of these things. You multiply the two and you add them up. It's as simple as this. Now, my slides are all wrong. Some of these quantifications, some of this pricing is easy. We talked about it last term and a little bit last week. Some of it is very hard because there's no price, and then you have to use monetary valuation methods. And last week I repeated what methods there are: the field preference method, travel cost hedonic pricing, the stated preference methods, contingent valuation and contingent choice, all with their drawbacks as well as strengths. Last week I talked about the importance of phrasing the question right. Do we do this exercise because we want to buy a better climate for our children and grandchildren, or do we do it because we impose a worse climate on them, right? Is it willingness to pay or willingness to accept compensation? Despite what Willy, whose picture I did not show last week, argued there's actually a big difference between willingness to pay and willingness to accept compensation. And I also talked about the difference, the reasons why these two measures are so very different, and why this is so very relevant for climate change. Because one of the reasons that willingness to accept compensation is much larger than willingness to pay is because we're talking about involuntary risks rather than voluntary risks. This is something that is imposed on us, and it's not something that we benefit from directly. Loss aversion, right, is the other reason why the two differ. One thing I did not talk about last week because I ran out of time is benefit transfer. So one thing that should have become apparent last term is that it's actually very hard to get valuation correct. That it's actually hard work to get anything like a reasonable estimate of the value of a piece of nature or a risk to human health. For that reason, valuation studies they're not rare. There's probably 10,000 or so of these studies have been done. But it's not anywhere near what we need, because climate change, as I argued last week, affects everything essentially. There's very few things that you can say that are not affected by climate change. So a few case studies, even if there's 10,000 case studies, will simply not cut it. We need comprehensive coverage of all the impacts of climate change. And not just for the recent past, for the last 40 years or so in which these valuation studies have been done, but we need it also for the future. And therefore, we need to extrapolate from the studies that we have to everything that we're interested in. The problem with this is but we're not very good at this. So this extrapolation is known in the technical jargon as benefit transfer, where essentially the benefit is you improve the environment, and the transfer is you estimate the value of one particular lake, and then you derive from that, you transfer that value to other lakes. And the question is, how good are we at that? Now, if you recall last term, particularly in the context of contingent valuation, where I talked about this at length, these valuations are actually highly context specific. I talked, for instance, about the difference in valuation of Lithuanians for the Baltic Sea, the difference between Lithuanians living in Lithuania and Lithuanians living in Poland, where for some reason Lithuanians in Lithuania like the Baltic Sea and are willing to pay a lot, but Lithuanians in Poland seem to have no interest whatsoever in nature. And that is actually explained because Lithuanians living in Poland do not trust the Polish government to do something useful with their money. So these values are often highly context specific, and that makes valuation, or the extrapolation of values, the benefit transfer, very, very difficult. And I'm going to show you one particular example. And this is from Denmark. What you're looking at, context. There are some 60 forests in Denmark, and you see them all. You can count the triangles to see whether it's indeed 60. It may actually be a little bit less. Let's make it 47 forests in Denmark. And this is the result from a travel cost study, which last time I argued is actually one of the more reliable methods of estimating at least the recreation value. So in 1977 they did a travel cost survey in all forests in Denmark. And they asked all sorts of questions. Where do you come from? How did you get here? Who are you traveling with? How much time did you spend to get here? How much money did you spend to get here? And so on and so forth. And then in 1997, they did basically the same survey, again, all 47 forests in Denmark, same list of questions. Where did you come from? How did you get here? How much did you spend? And so on and so forth. So, you have a pretty solid basis for a travel cost study, right? A detailed questionnaire, big survey. Now, that's not what you're looking at here. What you're looking at here is in the black triangles, the 1977 study was used to predict the travel cost values in 1997, 20 years later. And so on this axis, horizontal axis, we have all 47 forests. On the vertical axis, we have the error that was made. How well can you predict, based on 1977, what the value per square kilometer of forest, what the values would be? And you see that some of these predictions are actually pretty solid, right? A few percent off. Some of the predictions were like 750% off. That's pretty bad, right? That's pretty bad for a prediction.
But it's just a guess at that point.
There's no information, right? There's just no information. So this is Marianne Sanderson did this study. So this is what she did first, and then in gray she cheated. What she did was, this is a pure forecast. In the gray squares, Marianne cheated, and she sort of plugged in the demographic information of 1997. So I mean, these values depend on family size, right? People who come in larger parties are willing to pay more. People who come by private car paid less, definitely in time, than people who came by public transport. So here, see plugged in the changes in car ownership, the changes in family structure, the changes in income that we've seen from between 1977 and 1997 in Denmark. And based on the demographic information of 1997, but the valuation of 1977, this forecast popped up, or these forecast errors popped up. And you still see that there's some estimates that are pretty solid, but still you can be off by a factor 4. So this is pretty dramatically bad, right? The ability to forecast the value that Danish people attach to values over a 20-year period is not very good. And this is the easy exercise, right? It's 20 years. It's Denmark, which is a pretty stable society, right? Of course, for climate change, we are talking about impacts on the mangroves in Bangladesh, right? In the year 2100. So a much more dramatically, a much longer period and a much more rapidly changing society than Denmark over 20 years. So that is benefit transfer over time. Doesn't really work. And here are some benefit transfers over space. This is all within the United States. So they valued one lake for fishing and then looked at the lake next door and see, can we actually predict these values? Same for water quality between rivers. And this is all about water. Saltwater fishing, whitewater rafting. And this is actually a bit about biodiversity. And again, you're looking at a forecast error, right? So they did 2 studies, they studied 2 lakes, valued one, valued the other, and then say, based on what we know about lake number 1, can we predict the value of number 2, and how wrong do we get it? And again, you see that sometimes we get it right, but other times we get it spectacularly wrong, right? And this is within the United States. Now, most of these primary evaluation studies have been done in the United States, England. There's been a lot of studies, less on the European continent, very few studies in Africa, very few studies in South Asia, right? Very few studies in Latin America. If you can't forecast over space within the United States, what chance do you have to forecast from England to Cameroon, right? But that is unfortunately what we need to do. And that lies with the enumerative method, right? So, the numbers that I showed need to be taken with a grain of salt. What are my slides doing? So I talked about the enumerative method. There's all sorts of other things wrong with the enumerative method, and one of the things that is wrong with it is you treat these economic impacts as independent of one another, including you estimate the impacts of climate change on agriculture, and then you estimate separately the impacts of climate change on water resources, and you add them up, forgetting that 70% of fresh water is used in agriculture. So one way, I don't know why Ricciardo's face is here, one way to counter that is to use a computable general equilibrium model. Did I ask you guys last term what is a computable general equilibrium model? No, that. No, that was my masterclass in economics, where I asked, what is CG? So you've seen partial equilibrium models. In a partial equilibrium model, essentially you model one single market. Essentially what you would find in a partial equilibrium model is that if the quantity goes up, supply goes up, then the price goes down, right? And then the market finds a new equilibrium. That's a partial equilibrium model. The enumerative method actually ignores partial equilibrium effects, right? Quantities change, but you just use the old price, right? No price elasticities or anything of the sort. Now that is a partial equilibrium model. A general equilibrium model, or rather a computable general equilibrium model, does this for all markets and then connects the markets for individual goods in two ways. One, it imposes budget constraints on consumers. So people, if the price goes up in one market, then you spend more there. You probably buy a little bit less, but you spend more, and that means that you have less income left, less money left to spend in other markets, right? So there's spillovers from one market to the next through the budget constraint of consumers. So that is one link that you make between markets in a computable general equilibrium model. The other thing is that markets, production sectors, compete for workers and for capital. So if one economic sector is in trouble, say agriculture, you see your yields fall. So what is your response? You're gonna work harder because the demand for food stays up, right? The price for food goes up, but people will still want to eat. So farmers will be induced to produce more, to work their land harder. So they're gonna bring in more capital, they're gonna bring in more fertilizers, they're gonna bring in more workers to actually do that, to keep food production up. And that then implies that that capital is no longer available for other sectors, those workers are no longer available for other sectors, and of course if the demand for fertilizers go up, that means that those fertilizers need to come from somewhere. That has repercussions for the chemical industry, for the oil market, and so on and so forth, right? Because fertilizers are made of oil, right? So that's all in a computable general equilibrium model. The interactions in input markets as well as in output markets between different sectors of the economy, and then it's also linked up internationally. So if one country sees a sharp drop in its production of wheat, then other countries will try and make up for that, and you will see shifts in international trading patterns as well. So what you do in a computable general equilibrium model, if you want to study the impacts of climate change, is essentially you take the same sort of physical impacts that you would use in the enumerative method, and then you shock your computable general equilibrium model, that is how it is known technically, and see what comes out, right? So what you have is that because of sea level rise, part of your productive agricultural land disappears. You see a demand increase for the building sector to build dikes and seawalls. You see production of agriculture drop in certain sectors in certain countries, but perhaps go up in other countries and sectors. You see the productivity of labor going down because of heat waves and so on and so forth. And all those things you put in, you shake the model and see what comes out. The good thing about computable general equilibrium models is that they take into account all the interactions between sectors and have a whole lot of more adaptation, because now you can shift production, food production, from one country to the next. Another good thing about computable general equilibrium models is that the estimate that comes out is a theoretically consistent welfare estimate. These models are essentially just a lot of micro, and what comes out is the Higgsine equivalent variation, properly estimated. Whereas the enumerative method, just price times quantity, that's not a welfare measure, right? That's not how we define changes in welfare. It's just a direct cost. The bad thing about computable general equilibrium models is they typically have your standard micro representation of the world. So perfect markets everywhere, perfect information, rational consumers and rational producers. Pretty standard, no market power view of the economy. Go ahead.
What's the best computable general equilibrium model that's been is there like a particular really good one?
There now CGE people are not so much into rankings. Mine is better than yours. So it's not. There's essentially two models that are most widely used. That's the Irani G and the GTAP model, but that is more because they are convenient in their use, not necessarily because they are the best. And then there's of course a whole bunch of people who say that my model is best, but I don't think there's an objective yardstick that says this model is better than others.
I've always been a bit confused when people just sort of subside like imperfect markets, like irrational behaviors and stuff like that. 'Cause surely then it kind of lacks any real world application. Like what's the
Yeah. And
you gain out of it? Not specifically just in this model, but in like most.
no, there are indeed extensions of this where you introduce imperfections in a particular market. Absolutely, that has been done and can be done. The problem with that is that it actually becomes much more difficult to do, much more difficult to calibrate your model, much more difficult to interpret the results, because in standard micro everything actually is pretty clear. Once you get through all the math, everything has a clear interpretation and it's obvious what is going on. As soon as you introduce market imperfections, it is actually much more difficult to interpret what is going on and much more difficult to get your model to reproduce the observations that you have. And therefore what people do is that they introduce one imperfection at a time. So you assume perfect markets everywhere except for in the labor market, or you have perfect market everywhere except for in the oil market. That is how people do it, one imperfection at a time, and then you sort of like see what is going on.
Isn't that falling into like the usual social science chat?
This is an academic exercise, right? It's a controlled experiment.
I've just never understood why people don't try and incorporate big data and stuff like that into their sort of model.
Oh no, they do. So one application of computable general equilibrium model to the question of climate change is a model that incorporated 700,000 field experiments of crop yields. So they do. And Esteban Rossi Hensberg now runs a computable general equilibrium model on the grid with 30,000, I believe, economic units, rather than the usual 150 countries. So there is big data behind it.
Go bigger than that though, because that's like big. Don't get me wrong. Because I mean, if you're looking in like how a change in X results in Y, then yeah, obviously don't then go bring in loads of other.
Yeah. No,
if you're putting a like predictive model, then
I mean, these are the examples that I know.
Yeah.
What's his name? Oh, I forget his first name. Rauscher. No, it doesn't matter what his first name is. They bring in household surveys. So they have 30,000 individual households in the model. You can say, well, that's still not big data. You can bring in more, but bigger data, it's actually questionable what is the economic contents of this. And yes, you can scrape everybody's Twitter account and see what they're saying, but what is the exact economic meaning? But of course, if you use a household budget survey, and then in the US is actually one of the bigger ones, you have 30,000 different households. That's about the max you can get, right?
True.
And
Well, I feel
not
like we
quite
have
sure what you would
statistical-
learn of if you have 35,000 or 40,000
Well,
households.
that's why we have like analytical methods of determining whether like if the added observations sort of improves or if the bias variance trade-off just skews it in one way or another.
No, absolutely. We know about these things, and we know what sort of biases are introduced through these simplifications. Absolutely. Okay. So yeah, this is not the gold standard, right? This is good for certain things, but not for other things. And I think I was going to say the second problem, big problem with computable general equilibrium models, is that they are calibrated on the national accounts. And that implies that everything that is not in the national accounts is not in your model. And the two big ones are subsistence agriculture, right? That's not an economic transaction when you eat your own harvest. So it's not in the national accounts and therefore it's not in the model, but it's a big impact in the terms of the number of people affected. And the second thing that is not in there are the impacts on health and the impacts on biodiversity. So what is in there for the impacts on health are you getting ill, going to the doctors to buy medicine, right? Or going to the pharmacy to buy medicine, going to the doctors to get yourself fixed. That is an economic transaction, that is in there. But what is not in there is how miserable you feel, right? So, good for some things, not for other things, right? Now, another thing that people have done, this is actually the time that is up there, is use the so-called Ricciardi method, and that is why Ricardo's face is here. And they estimate the relationship between some economic activity or some economic welfare indicator and climate change over space. And then assume that this relationship holds over time. So the first application of this to climate change is a study in the United States where they ran a regression of the value of the value of agricultural land on average rainfall and average temperature, and found a nice parabolic relationship that if it's very cold it's not very good for agriculture, if it's too hot it's not very good for agriculture either, but in the middle you sort of have this Goldilocks zone where it's actually brilliant for agriculture, right? So that is a relationship you find over space, and then you can just say, well, what if climate changes? We just impose the same relationship. A good thing about this statistical method is that unlike in the enumerative method, you don't have to make assumptions about adaptation. Actually, most of the physical impact studies that I talked about last week either assume no adaptation whatsoever, and we talked about that at length, but there's also a few studies out there, and we started talking about this, where adaptation is based on the assumption of perfect information and fully rational behavior and perfect markets. And then, of course, you have a very optimistic way in about how people adapt. Now, the statistical method doesn't make assumptions about how people adapt, but just look at how people have changed, in this case, how farmers have changed their behavior in response to the different climates that they live. So you have a realistic representation of how people respond to the climate. So that is good. The big problem with the assumption that you estimate the relationship over space and assume that it holds over time is that time and space are not the same thing, right? And there's two crucial problems. One is that you hold technology and institutions constant, because they're constant over space. If you do this study for the United States, they all have the same trade barriers for agricultural products, because that is the same in the US. You have sort of like the same technological support for farmers, because that is roughly constant over space, but it has varied greatly over time. The other thing that is particularly problematic is trade. So what you see in the United States is that people grow wheat in Maine and citrus fruit in Florida. And that is not because people in Maine only eat wheat and people in Florida only eat citrus fruit. No, you see trucks going up and down the Atlantic coast to take the wheat from Maine to Florida and the oranges from Florida to Maine. And of course there's differences in the value of land, right? It's much more profitable to grow citrus fruit than it is to grow wheat, right? Which is a bulk product that competes, or used to compete, with Ukraine and Russia, right? Now if you then sort of observe this relationship and then you sort of like turn it 45 degrees and say, well, this also holds over time. And essentially what you're assuming that it's just as easy to transfer agricultural goods over space as it is over time as it is over space. Now we can ship food into the future, but at a fixed rate, and it actually pretty quickly degrades in quality. We can't eat next year's harvest, right? That does not fill your stomach. Does not fill your stomach or your tummy, not the two together. So again, strengths and weaknesses of this method. This so-called Ricciardi method has also been used to directly estimate self-reported well-being and in relationship with climate. And then finally, there's one study which is an elicitation method where essentially people were interviewed. What do you think the impacts of climate change would be? The problem with the result that I showed you is that it's from 1994, at which time nobody could reasonably claim to be an expert in the economics of climate change. So that is where these studies come from. That is what we have found. So what does this set of studies tell you? There's a number of messages from this graph. The first, and to some people surprising or annoying, is that the initial impacts of climate change may be positive. That the first degree or so of warming actually brings economic benefits. The reasons for this is threefold. One, and actually I talked about all three. One, if it's warmer in winter, you need to spend less money heating your home. That's a clear positive. It's actually pretty big because people spend a lot of money on that. I don't need to remind people in England of this. The second is a reduction in cold-related deaths, which is actually much larger than the increase in heat-related deaths, definitely in the more northerly parts. And the third is CO2 fertilization that I also talked about last week. If there's more CO2 in the air, then plants grow faster and are more drought resistant. So those are the three positives, and that explains why the initial impacts of climate change are perhaps positive. But then if you move to more pronounced warming, you actually see that the negative impacts start to dominate. Spread of tropical disease, sea level rise, those sort of things. As well as, of course, the increase in demand for cooling in summer. Now, these initially positive impacts are sunk in the sense that they will happen regardless of what we do. So 0 is pre-industrial, and the world has already warmed by, depending on which estimate you believe, by 1 degree, maybe 1.2 degrees. Some say even 1.4 degrees. And you actually see that the incremental impacts start turning negative around 1.3 degrees of warming. We're not going to stop. The climate change is not going to stop at 1.3 degrees of warming if we are still below that. In itself is disputed. So from here on, all extra warming reduces average welfare, right? So the fact that there were benefits, or there may be still some benefits in the next decade or so, that's actually irrelevant. From now on, all extra climate change is bad for us. So that is the first thing that you see. Second thing that you see is that there is actually, I talked about 4 different methods, all with their strengths and weaknesses. People actually roughly agree on at least the order of magnitude of these impacts. So you can pick apart every individual study, but it doesn't really change the picture. The third thing you see is the order of magnitude. And the order of magnitude is that 2.5 degrees of warming would maybe lead to a welfare loss that is equivalent to losing 1.3% of your income. That's a problem, right? But it's not the biggest problem in the world, right? 2.5 degrees maybe takes you to 2080 or so. So 1.3% of climate change, a century of climate change is about as bad as losing a year of economic growth. That's the order of magnitude that we're talking about. Which is a problem, right? But Japan has been going without substantial economic growth for a few decades now. People in Japan are still fine. And that is a bigger problem than what is seen here, right? And the problems in Japan are, of course, nothing compared to the problems that the people in Ukraine have at the moment, right? So climate change is not the biggest problem of humankind. It's also, and I'll come back to that next week, it's also not the biggest environmental problem of humankind. The final thing I want to say about this graph is the range of uncertainty that you see. And this is only the 70% confidence interval that is depicted here. And first thing is that the uncertainty is large, right? See the enormous range. This is no surprise here, right? I talked about a lot of the uncertainties about climate change and so on and so forth, and about valuation of climate change. So no surprises there. And of course we are talking about forecasting things 100 years into the future. And the idea that we know what the world will be like at the moment, the idea that we know what 2023 will be like is difficult to imagine, let alone that we know what 2030 or 2100 will be like, right? So yes, this is a hard problem. So uncertainties, if uncertainties were small, then you should laugh at me, right, for being over confident. Second thing that you see about the uncertainty is that it's asymmetric. That is, the upper bound is much closer to the central estimate than the lower bound. And that has two basic reasons. One is it's actually three. One is the uncertainty about climate itself. So if you read IPCC reports, then for a very long time now, the forecast is that if the atmospheric concentration of CO2 were to double, then the world would warm by 2.5 degrees, central estimate, with a range of 1.5 to 4.5, right? So in the physics already, you see that negative surprises are actually much more likely than positive surprises of the same magnitude. And that is then amplified by the fact that most of the impacts are non-linear. So 4 degrees of warming is more than 2 times as bad as 2 degrees of warming, right? And 2 degrees of warming is more than 2 times as bad as 1 degree of warming. And then if you put those things together, things can actually get out of hand. And what you've read in the media, undoubtedly, is plenty of stories of people saying of predicting catastrophe because of climate change. But I bet you've never read a story that climate change will make us all blissfully happy, right? That just doesn't happen. It's very easy to paint pictures of things going completely wrong because of climate change. My favorite horror story is Bangladesh. I'll come back to Bangladesh after the break. Sea level rises by 1 meter, then you need to evacuate about 1/3 of the land area of Bangladesh, about 50% of its people. Where would they go, right? They can move up into the northerly parts, the higher parts of Bangladesh, but the Bengalis and the people who live there actually don't really get along, and there's already a lot of sort of low-level civil conflict going on in the north of Bangladesh, but much more likely they would follow historical patterns, that if there's trouble in Bangladesh, then Bangladeshis move into India. And an influx of 30 or 50 million Muslims into India, you can say that would not sit well with India, right? And you could predict, definitely in the current government, you could predict a pretty nasty response, and would probably lead to war or civil war. Civil war in India, perhaps war between India and Bangladesh. And then of course the response of Pakistan would be that they would come to the rescue of the Muslim brethren, right? And then you're talking about nuclear war on the Indian subcontinent. You can sort of like see this chain of events happening because of climate change and sea level rise, right? So that would be here. That would be pretty dramatically bad. At the same time, you also see the enormous uncertainty in this range, in this cascade of events, right? Really, would this happen? And of course, the picture that I paint is plausible in 2022. But we're not talking about a meter sea level rise in 2022 in Bangladesh. We're talking about a meter sea level rise at the end of the century, in 80 years from now. And of course, if we think back 80 years back into the past in Europe, Europe was at the brink of war, right? God, that example doesn't work anymore, right? Because Europe is not quite as peaceful as it was last year when I last told this story. But circumstances change, right? And at the moment it's completely unimaginable that if northern Germany would have to evacuate because of sea level rise, or the Netherlands would have to evacuate because of sea level rise, that would lead to war between France and Germany, right? That is completely unimaginable now. And hopefully in 80 years' time it will be completely unimaginable that Pakistan and India would go to war, right? Almost at the break. So, showed you the numbers, what is wrong with them. There's a lot of things that are missing. The biggest one that is missing is tourism. We spend Rich people spend 10% or more of their income on tourism and recreation and leisure, and a lot of that is directly related to weather and climate, right? We don't go to Spain because of the food. I hate Spanish food. We go for the climate, right? But that is still not included in these studies. Interactions between impacts, I talked about. Stylized adaptation, either perfect adaptation or no adaptation at all. Low probability, high impact. I talked about nuclear war on the Indian subcontinent is not included. And a lot of the knock-on effects, I'll talk about that next week. If you change these things, you also have knock-on effects on economic growth, for instance, is not included in there. And a large melting of the Greenland ice sheets and of the thermohaline circulation, or stoppage of the thermohaline circulation, and therefore the Gulf Stream that keeps Western Europe warm is all not included there. So these studies are far from perfect, but this is what we have. And this is what we know about the total economic impact of climate change. So far we talked about, or I did most of the talking, about the total economic impact of climate change, which is nice, but irrelevant, right? As soon as you do optimization, you're interested in the marginal. And the social cost of carbon is simply the marginal damage that is done if you emit an additional ton of CO2. And the way you calculate this is that essentially that's the exercise that there is for this week, right? So you take a scenario of climate change and the impacts of climate change, and then you run the exact same scenario but with a little bit of extra CO2 added to the atmosphere. You see how that changes climate, you see how that changes the impacts, and you take the difference between the two streams and you calculate a net present value of that, and of course then you need to normalize by the change in emissions. If you do this along the optimal trajectory, then this marginal damage cost, or the social cost of carbon, is equal to the Pigou tax, right? It tells you how much the price of emissions and therefore the price of energy should go up. And it's a normative concept then, right? It tells us what to do. It's also a normative concept because you also need to decide on how much you value things, and you need to decide on how to discount the future, right? So it's doubly normative. It does not just tell you what to do, but it also reflects how much you care about things, and I'll get back to that extensively. So that's the marginal damage cost, or the social cost of carbon. I'm going to look a little bit at the estimates that we have of this thing. I told you before that there's 27 estimates of the total impact of climate change. When I did the counting here, there were 2,700 estimates of its first partial derivative. And you may think that is strange, because you have 27 primary estimates, and then you take its first partial derivative, you have 27 estimates, right? Not 2,700. The reason for this is that there's many more degrees of freedom. And what you can do, what you need to do, is somehow you need to translate these estimates that we have, these blue dots, into an impact curve. And there's many ways of doing it. This is a slightly different curve than what you saw before, but it's also very different because now it's expressed as a function of time rather than as a function of climate change, or the change in the global mean surface air temperature. So that is the first thing that is different, right? You, instead of having a dot, you need to fit a curve through that dot. And the red line that you see here is just one way of doing that, and you can think of many different shapes and forms that could take. But also, and here I express it as a function of time, it immediately means that I made an assumption about how the global mean surface air temperature will change over time. And that means that I made assumptions about how much emissions there will be, right? And also how climate would respond to those emissions and the carbon cycle. So I made a lot of assumptions already, right? And all these assumptions are disputable, and different people make different assumptions there. Now, I talked about the first 4 points. I showed you the global impact. There's of course also a regional pattern behind that I will come to. There's also a sectoral pattern behind that. And again, different people can make very different assumptions that are just as credible about this. And then of course people may strongly disagree. If you have different regions, how do you aggregate impacts across regions? We'll talk about that in week 9. And how you aggregate over time, how you deal with a large uncertainty, and so on and so forth. So that explains why, even though there's only few handfuls of estimates of the total impact, there's a great many estimates of the social cost of carbon. Now, the good thing about a great many estimates is that you can, I should have updated this, is that you can do fancy statistics, and in this case what I showed to you is a kernel density estimate. So this is essentially a probability density that is fitted through all these observations. And essentially what it says is that the most likely value is something like 40 dollars per ton of carbon, and then there's some probability that is negative, and then the probability that it's sort of in the range of 400 or 500 is actually pretty small, right? That is how to read a probability density. Now, this is again right skewed, just as the uncertainty about the total impact is right skewed, that negative surprises are much more likely than positive surprises. You see the same here. The mode is around 40, but then there is this very substantial probability mass to its right and a much smaller probability mass to its left, which then implies that even if the mode is 40, the mean is around 63, right? Again, this sort of like emphasizes the negatives, right? That's what this tail does here. The other thing that you see is that there's free curves, free probability densities. In brown, I use a 5% discount rate, or a 5% consumption discount rate, 3% utility discount rate, or the pure rate of time preference. That's what PRTP stands for. If you use a lower discount rate, 1.5 or even 0.1, then the impacts go up. You see that in the numbers that you see there. And this is a sample split, right? Some studies use a high discount rate, some studies use a low discount rate. The mean impact goes from 63 to 390 if the discount rate, the utility discount rate, halves, and it goes up to 630 if it falls even further to close to 0. Now this is exactly as you would expect, right? So the lower the discount rate, the higher the value you place on the future. And the higher the value you place on the future, the higher the value you place on climate change, right? Because it's mostly in the future. So that is exactly what you would expect. There's another thing going on. The number in brackets is the standard deviation of the social cost of carbon. And you see that that also goes up, and actually goes up a bit faster even. And you see that also in the shape of the probability density function. Essentially, this is a probability density function, right? The brown curve. This is a curve. It's high in the middle, it's low at the end, right? That is what you would expect a probability density function to look like. But if you look at the blue curve or the green curve, it loses essentially the features of a probability density, like it just doesn't want to go to 0. And you see that also then in the standard deviations. They're also very, very big. The reason for this is that is a bit subtle, and that is that the lower the discount rate, the more you care about the future. But the implication of this is that you also need to look further into the future. If you use a high discount rate, then after 100 years everything is 0, so it doesn't matter. If you use a low discount rate, then things after 100 years are still important. And of course, if you need to look 100 years into the future, you see a lot more uncertainty than if you only look 30 years into the future. So the lower the discount rate, the greater the uncertainty becomes, because the future essentially grows larger. Right? Forget about this. This was the price last year. The price of CO2 permits has gone up very considerably over the last year, and it has completely collapsed in the last week. So I haven't got a clue what the price is. May actually be correct. Again, until recently, the price in the EU was roughly equal to the social cost of carbon. The implication of that for a relatively low discount, for a relatively high discount rate. The immediate implication is, because the price of CO2 permits is much higher in the EU than elsewhere in the world, apart from the UK, is that the rest of the world undervalues CO2, and the EU get it roughly right. And that is the reason why this is here. But as I said, I don't know what the price of carbon is today. It's 60 euros per ton of CO2, but that is not the same as dollars per ton of carbon, right? I'm not going to do that conversion live. So this is the number that matters for policy, right? This is the marginal impact. The other number that matters for policy is, well, if the social cost of carbon is 60 in the year 2022, what should it be in the year 2023? Of course, just as important than in the year 2024. So the same set of studies have also estimated how the social cost of carbon changes over time. And this is another kernel density that was estimated. This almost looks normal, right? This is a proper bell curve, unlike the other one. There's a little bit of right skewness here, right? This tail is a little bit fatter than this tail. The central estimate is that the social cost of carbon, the carbon tax, should increase by some 2% per year. So, sort of your first approximation to an optimal climate policy is to start today at 60 or 80 dollars per ton of carbon and let it increase by 2% per year. That is sort of your optimal policy. So that is where we are. The thing that I did not talk about at all is the distribution of impacts, and I have 25 minutes to do so. I showed you this curve now a couple of times. This is what happens to the welfare of the average person on the planet. Go ahead.
Quick question regarding social cost of carbon. So with that annual growth rate of the taxes, so surely when they have to estimate that, wouldn't they also need to predict varying inflation rates?
This is in real terms.
Oh, okay.
So inflation is stripped out already. So I showed you this one. This is for the average person on the planet. It is not particularly relevant because very few person are on average. The same data set will also tell you the distribution of impacts over the countries in the world. And that pattern looks something as follows. So this is for 2.5 degrees of warming. So that is where we have most information, right? That's why I focus on 2.5 degrees. The vertical axis is still the welfare equivalent income loss, so it makes you feel as if you have lost your income rather than you haven't lost your income. Now the horizontal axis is the average per capita income in the 200 or so countries in the world. And this is a log scale, right? So we go from 100 to 1,000 to 10,000 to 100,000. And you see a very clear pattern here. Large negative impacts in poor countries, mostly positive, or at least much smaller impact in rich countries, right? And there's a few exceptions to this rule, right? You have Singapore, which is pretty rich, but also tropical and an island, right? And Bhutan and Mongolia. I think this is Mongolia and this is Bhutan, which is very poor but also very cold, right? But by and large you see that poorer countries are much more vulnerable to climate change than our hotter countries. Now there are 3 basic reasons for this, and the first is exposure. If you look at the structure of a poor country in Africa, then 40% of GDP is in agriculture, 70% of the workforce is in agriculture. Directly exposed to the weather, very vulnerable to climate change. If you look at the United Kingdom, where do we make our money? In publishing, in finance, insurance, office jobs, people sitting at home or in office buildings shielded from the weather, right? Only 1%, 2% of income comes from agriculture. So the structure of the economy determines your vulnerability to climate change, obviously, and the structure of the economy is very different in poor countries than in rich countries. So that is one explanation. The second requires a little bit more thought. This is the same information, but I swapped the horizontal axis. Now we're looking at the current temperature. And what you see is that hot countries see negative impacts and cold countries see positive impacts. And of course, hotter countries tend to be poorer and poorer countries tend to be hotter. The reason for this is twofold. One, a lot of the systems on which we depend, the sort of biological systems on which we depend, are closer to the biophysical limits in hot countries. Not so in cold countries, right? So that is one reason. The second reason has to do with adaptation. So if you wonder what the future will be like if Brighton were 3 degrees warmer, then you look at Marseille, Bordeaux, Barcelona, right? Those are places that are 3 degrees warmer than Brighton. You notice that people do things differently there, right? They have dinner late at night. They have white houses rather than black houses, as you see here. You have buildings that are designed to keep the heat out rather than the heat in, as we do in England, and so on and so forth. There's a whole range of behavioral and technological differences between here and northern Spain, southern France. But if you wonder what Brighton or the south coast of England would be like with 3 degrees warming, you essentially look at those places and you can copy their behavior and their technology. And that's an easy thing to do. Maybe hard to swallow for some of the more bigoted Englishmen, that they will need to be more like the French or the Spaniards, but it's feasible economically, technically, and so on and so forth. If you live in the hottest place on earth, Singapore, Dar es Salaam, places like that, and you can't copy somebody else's behavior. You can't adopt somebody else's technology because they don't exist. You need to invent everything from scratch, which is much, much more difficult, right? And that is the second reason why hotter countries are much more vulnerable to climate change because they don't have ready-made adaptation for them. And adaptation, as I argued last week, is crucially important. The third reason is a lack of adaptive capacity. That poorer countries have a lower adaptive capacity than have richer countries, and that requires some unpacking. So adaptive capacity is just the ability to adapt. Something changes and you need to adjust your ways. How good are you at that? Adaptive capacity depends on three key things. One, you need to know how to do this technologically. So if you're confronted with sea level rise, your best response is to build a dike or a seawall. So you need to know how to do that. Now this is a bad example. The first dikes were built probably by the Sumerians 5,000 years ago, and it is a pretty basic technology that most people know, right? And anybody who's played on the beach as a child would know the basics of this, right? Because we've all built sandcastles and see them wash away, right? We're not very good at it, but we sort of got the basic principles there. The second thing that matters for adaptive capacity is that you need to be able to pay for these things, right? Because knowing how to build a dike is no good if you can't afford to pay for it. Which both immediately put poorer countries at a disadvantage, right? There's just fewer technologies around and fewer people who actually know how to operate these things, and there's simply less money to go around. And the third condition is the ability and the will to use these resources to protect the people. And this is actually, I think, the most important one of the three. And I'm going to illustrate that with one example. And that is the difference between the Netherlands and Bangladesh. The Netherlands and Bangladesh are very similar. They're deltas, they're low-lying, very densely populated. There's the risk of flood from the sea, there's the risk of flood from the rivers, there's the occasional big storm, right? The Netherlands and Bangladesh are very, very similar if you look at it like this. But yet when we talk about sea level rise, we worry about Bangladesh, but we don't worry about the Netherlands. Not at all, right? Why is that? Well, let's look at the determinants of adaptive capacity. What you're looking at in blue is per capita income in the Netherlands over the period 1700 to 1900. You see, basically stagnant economy. Then Napoleon comes along, messes it all up, but sets the Netherlands on a steady path of economic growth after that, right? These are the Napoleonic years when there was no economic records being kept. In orange, you're looking at Bangladesh starting in the year 1950, right? And this is the year 2018. And actually what you note is that in 2017, Bangladesh was about as rich as the Netherlands was in 1850. And nowadays,
1700s
this is years of the Netherlands. And then Bangladesh is 250 years, so you need to add 250 to 1700. And you see that Bangladesh nowadays is richer than the Netherlands was in 1850. Now, why do I say 1850? Because 1850 is the year that modern dike building started in the Netherlands. So this is not, economic resources is not an issue, right? Bangladesh is richer now than the Netherlands was then. Slightly richer, but still. Is technology an option? Well, we actually don't have pictures of the Netherlands in 1850 because the photograph had yet to be invented. But we do have pictures of the Netherlands in the 1930s and dike building in the 1930s. This is when closure dike that ended the Southern Sea and turned it into the Icel Lake was completed. And what you see is some drag lines. This is actually driven by steam, some mechanization, but you see an awful lot of men with shovels and wheelbarrows, right? This is how dikes were built in the 1930s in the Netherlands, right? Essentially by hand. Now, if you look at dike building in Bangladesh 10 years ago, you still see an awful lot of people, but you also see concrete, right? And you see drag lines, and so on and so forth. It is a much better technological situation. What you don't see on this picture is that the Bangladeshis have access to computers and computer models of sediment flows and those sort of things. They have access to satellite pictures of what the coast looks like exactly, and so on and so forth. They just know the situation much, much better. So technology in Bangladesh in 2022 is far superior to technology in the Netherlands in the 1850s, right? In the 1850s, engineering was essentially artisanal, essentially just like guys, guesswork, how things really work, whereas now everything is computer modeled and tested, and so on and so forth. So, I should have updated this slide. Economically, Bangladesh is actually slightly ahead of the Netherlands, and technologically, Bangladesh is far ahead of the Netherlands in 1850, right? So what is the big difference? Why do we worry about sea level rise in Bangladesh? Well, first, corruption is terrible. A lot of money that is spent by the Bangladeshi government, including money spent on coastal protection, disappears into Swiss bank accounts and mansions in London, right? That is where Bangladeshis store their money. Politics in Bangladesh used to be very antagonistic. Essentially, you had this constant change of power between the two main parties. And what politics was about was two things. First, it was about getting rich as quickly as you can, because you can lose power very quickly afterwards. And second, it was about getting even with your political opponents, making sure they end up in jail or worse. And then as third concern, oh yeah, you were also in charge of the country and trying to do something good, right? But that was an afterthought. Bangladesh is nominally democratic. It actually has improved somewhat, and because one power party now has pretty firm control over. It's essentially turned from a democracy, a very unstable democracy, into a pretty authoritarian place. So that is somewhat better, and that explains why Bangladesh is now growing so very rapidly, right? Essentially, one party took over. Bangladesh is nominally a democracy, but even though the vast majority of people is poor, they don't carry much weight in decision making, because most of them are so poor that you can very easily bribe them to vote for you, which is going on all the time. And they're also very poorly educated. This was one too far. So what you're looking at here on the left hand side is the darker the color, the poorer the people. So this is where the poor people are in Bangladesh. This is in the Sundarbans, right on the coast. And here, right on the river, right, this is the low-lying deltas. And here you're looking at the places that are particularly susceptible to flooding, here from the sea and here from the river. And you see a very clear pattern here, right? The poor live where the flood risks are, or the flood risks are where the poor are, right? And this goes back to hedonic pricing, essentially, right? If you're rich enough, you go live in the hills north of Dhaka, right? Actually, it's slightly cooler, but flood risk is down because you're higher up. Or you go live in London, right? Which is what rich people in Bangladesh do. So their house prices go up, right? The rich outbid the poor. Poor are removed from there, and the poor have nowhere to go but where the land is cheapest. And where the land is cheapest is, of course, where it's the silliest place, the most dangerous place to live, which is in the coastal flats and in the floodplains of the river, right? So that is economics. There's also a cultural aspect here, and that is that people are so poorly educated that they do not make the connection between the floods and the actions of politicians. And if you do surveys in Bangladesh, then you would find that people say that a flood is a punishment from Allah. It's not because the Prime Minister did something stupid or didn't do what they were supposed to do. No, this is a punishment from Allah, right? Now, this has nothing to do with Islam. There were similar surveys done in the 1870s in the Netherlands, going back to the main story, where people said that floods are a punishment from God. And actually also people who took a step further and said that dike building gets in the way of God's will and is therefore blasphemous, right? So it has nothing to do with Islam whatsoever, everything to do with poor education and so on and so forth. So these are the main reasons why Bangladesh is so very vulnerable. There's an elite who doesn't care about the people, and even if they would care, they probably do not have the capacity to do these things, because as soon as they start allocating money to dike reinforcement or dike building, that money would be stolen by some lower official, right? Now, returning to the start of the story, why did dike building start in the Netherlands in 1850? It's not that in 1850 the Dutch all of a sudden discovered that there were floods, right? Floods had been going on in the Netherlands for a good part of a millennium at that point, but nothing was done. What happened in the Netherlands is the following. This is a very brief history. In 1848, the people of Europe, Western Europe, rose up against the old elites. In France and in Germany, also in the Netherlands, and as a result there was a major reform of politics. A new constitution was introduced in 1848, which did two things. One, it formed a strong central government, rather than the Netherlands is plural, because it used to be a confederation, not even a federation, right? There was just the 7, later 11 provinces that basically went their own way and had a joint foreign policy, right? But that was basically it. But first time there was, well, second time Napoleon also introduced a central government, but that was not to last very long. Strong central government, so that you can actually have the resources and you can provide public services, public goods in a good way, in a proper way. And the second thing is that until 1849, the Netherlands was essentially ruled by what we now call oligarchs. It was essentially run by and for the rich merchants. That ended in 1849, when for the first time there was a government that was broadly representative of the people. broadly, I say, because women didn't count, obviously, it's 1849, and also Catholics were out, right? So it was broadly representative of the male Protestants of the country. And the first thing that the new government did was go after public enemy number one, flood risk, right? And that is why in 1850, rather than before, not in response to floods or anything, but in response to political events, modern dike building started in the Netherlands in 1850. So that is the problem in Bangladesh, right? It's simply a government that is unsuited, unable and unwilling to solve these problems. And I picked on Bangladesh. There's no Bangladeshis in the audience or in the, and Parvez is also not from Bangladesh, as we established last week. You can say give the same story for Cameroon or Central African Republic or Venezuela or any country like that, right? The core of the problem is poor government. That's all I wanted to say for this week.